The following are examples of how best load software can be used to optimize unit load designs in order to improve performance and safety while reducing cost and creating new supply chain efficiencies. This unit load is comprised of a new 48-inch by 40-inch pallet and interlock double-wall BC flute corrugated containers. The goal is to reduce overall cost of the unit load. Prior to manipulating the unit load design, it is important to understand the current performance criteria. The current pallet design uses 9/16" thick top deck boards, 5/8" thick bottom deck boards, and 1¼ stringers, for a total of 12.6 board feet of lumber. The storage and handling conditions include free span racking across the pallet width, handling with forked equipment in both directions, and stacking 2 unit loads high in warehouse floor storage. The predicted maximum safe load for the critical support condition just exceeds the required payload for the pallet. The predicted compression strength for the double wall BC flute corrugated container exceeds the target compression strength by 282 pounds. However, we cannot simply adjust the box design to a single wall C flute, as we see the predicted compression strength drops below the target compression strength. So we must focus on the interface between the pallet and the packaging system. Here, we can see which box corners are supported versus unsupported and which boxes are under the highest stress. Keeping the target compression strength of 444 pounds in mind, we will reposition certain deck boards to better support box corners. By doing so, we have reduced the target compression strength by 77 pounds. With the pallet design still in consideration, we want to also evaluate how we can increase the deck stiffness while not increasing the cost of the pallet. By increasing the stiffness of the deck, we can reduce the maximum uniform compression stress of 9.1 psi. One way to do this is by adding a 4th stringer to the pallet design. This effectively reduces the span between stringers, stiffening the deck. We will reduce the width of the stringers from 1¼ to 1⅛, and we will adjust the positioning of interior stringers to comply with pallet jack equipment. Furthermore, we will reduce the top deck thickness from 9/16" to 1/2 inch, and the bottom deck thickness from 5/8" to 9/16". Here we can see we've maintained the overall board footage of 12.6 board feet, and we've improved the performance of the pallet in the critical support condition, as well as other support conditions. Now, we attempt to reduce the box design from a BC flute to a single wall C flute. we can see that we're still slightly under-designed with the current board grade. However, before we manipulate the board grade, we can also factor that the unit load was 100% interlocked. If we interlock the top two layers, leaving the bottom three column stacked, we get compression performance as well as stability and a satisfactory predicted compression strength compared to the target compression strength. The overall reduction in cost for this unit load was $11. The next unit load is comprised of 5-gallon plastic pails unitized on a 48-inch by 45-inch 4-stringer pallet. The goal is to reduce the maximum uniform compression stress on the pails in order to reduce the cost of the pail. We will begin by evaluating the pallet design and performance. The current pallet design uses 5/8-inch thick top and bottom deck boards, as well as 1.5-inch wide stringers, for a total of 16.8 board feet of lumber. Storage and handling conditions include free span racking across the pallet length, handling with forked equipment in both directions, and stacking up to 3 unit loads high in warehouse floor storage. The predicted maximum safe load for the critical support condition exceeds the required payload, indicating this pallet has adequate strength and stiffness. If we then move to the interface between the pallet deck and pails, we can understand which pails are under highest stress, considering that 2 interfaces modeling this static stress are presented simultaneously. The uniform compression stress indicates a maximum stress of 34 psi. In order to reduce the cost of the pail, we must reduce the wall thickness, and to do so, reduce the applied stress on the unitized pails. If we proceed to the pallet design, one aspect we can take advantage of is adding a double wing. This effectively reduces the span between stringers, stiffening the deck. We can also reduce the spacing between deck boards by adding 1 interior deck board to the top deck and reduce the thickness from 5/8 to 9/16. We will do the same for the bottom deck. If we then proceed back to the pallet performance, we understand that we have increased the performance in all storage and handling conditions, as well as maintained the total board footage. Furthermore, the stress on the pail has been reduced to 15.4 psi, effectively allowing us to reduce the pail wall thickness from 90 mil to 80 mil. The final unit load is comprised of shrink-wrapped 24 packs of plastic water bottles unitized on a 48-inch by 40-inch pallet. The goal is to reduce the applied compression stress on the water bottles to effectively reduce the amount of primary packaging damage and leaking bottles. We first want to evaluate the interface between the pallet deck and the packaging system, where we can see which of the water bottle packs are under the highest stress, keeping in mind two static stress interfaces are modeled simultaneously. And furthermore, the maximum uniform compression stress distribution, where we can clearly see up to 12.2 psi in two specific locations. Before modifying the pallet design, we may want to consider the stacking configuration being used. Here we can see the first layer of water bottle packs on the top deck. And if we look in the geometric fit column, we can see there are options with lower maximum uniform stresses that maintain the amount of packaging per pallet. If we simply click on another option, we can see how the stacking pattern has been reoriented, and we can do the same for the entire unit load. Once we report back to the stress distribution, we can see right off the bat that it is more uniform, and it is also 2.2 psi lower in maximum applied stress. This can be used to reduce the amount of leaking water bottles.